Welcome back to Module 23 of Engineering Vibrations and Introduction to Single Degree of Freedom Systems. Today's outcomes are to solve for the roots of the characteristic equation for the differential equation of motion of a simple single degree of freedom oscillator undergoing free damped vibration. Then we're going to define what's called the critical damping constant, and finally we're going to classify the different cases of damping. So here's where we left off last time. This was a model of a damped system, a free vibration damped system. We used, as an example of a real-world system, the golf cart, the back quarter panel of a golf cart with its suspension system. We came up with this differential equation of motion. So now, for this type of a model, we want to solve the differential equation of motion, and to do that, we'll use the same technique we did before, which is the method of undetermined coefficients. I'll assume a solution. Since the differential equation of motion involves a coordinate y and its derivative and second derivative, we need a function that comes back with the same form after taking derivatives, and that's an exponential form. So I'm going to assume that y as a function of t is some undetermined coefficient a e to the lambda t. Now, having assumed that solution, I'm going to substitute it into my differential equation of motion, and I end up with the mass times a, and with the second derivative, lambda comes down twice, so it's lambda squared e to the lambda t. And then for the damping term, I have c times a, and with the first derivative, lambda comes down times e to the lambda t. And then I have k times y itself, which is assumed to be a e to the lambda t. And that all has to equal 0. And so here I factored out the a e to the lambda t. There's two ways to satisfy that equation. One is if a e to the lambda t equals 0, but that means that y of t is equal to 0, so there's no displacement of y, and so that's a trivial solution. There's really no motion. And so the more interesting case is when we set the quantity in the parentheses equal to 0. That's called the characteristic equation, where m lambda squared plus c lambda plus k equals 0. And so here's my characteristic equation. I went ahead and just rearranged it. It's a quadratic. I'm going to, by rearranging it, I'm going to call k over m the square root of the natural frequency squared, and c over m is the coefficient for the lambda term. And so we can solve for the roots. We know the solution for a quadratic formula. It's minus b plus or minus the square root of b squared minus 4ac all over 2. And in this case, it's as shown, and I get two roots, plus and minus, for the quantity underneath the radical. And so there's some different situations here. If the quantity underneath the radical is a positive value, it's a positive value, but it's less than c over 2m because we're subtracting omega natural squared from it. And therefore, you're going to end up with two real negative roots. Now, if the quantity underneath the radical is equal to 0, or underneath the square root is equal to 0, same thing, what happens then is you get two negative repeated roots, minus c over 2m and minus c over 2m. Now, if the quantity under the radical is negative, you have a negative number, when you take the square root of that, you're going to get an imaginary value, plus or minus an imaginary value. So I have minus c over 2m plus or minus I times a value. So those are complex roots. We're going to define critical damping, or the critical damping constant, for the transition where the radical actually goes to 0. So between these two situations where the value under the radical is positive or negative. So when the square root, the quantity underneath the square root sign equals 0, that's going to be the case of critical damping. And so if you take the quantity underneath the radical and set it equal to 0, you have the critical damping constant is 2 times the mass times the natural frequency. So we're going to define the critical damping ratio and give it the symbol zeta. And zeta will equal the actual damping constant, C, as the ratio to the critical damping constant, C sub C, which we found to be 2m times the natural frequency. And so with that critical damping ratio, we now have several cases of damping. If zeta is equal to 0, we have C equal to 0. That means we have no damping. That's an undamped system, and that's what we've been solving up until this point. Now, if zeta is less than 1, we call that an underdamped system. And that's a system where we have decaying oscillations. And so that's the system like we saw with the golf cart, where I jumped up and down and it was a decaying oscillation. There's other examples. Let me give you another demonstration here. Okay, and this is where I'll put in the demonstration. Okay. The next case of damping is when zeta equals 1, we call that critically damped, so that the actual damping equals the critically damped constant. And we can have an overdamped system where C, the damping constant, is greater than the critically damped system. Here's an example of an overdamped system, which is a door returning to equilibrium with a damper. So a critically damped system or an overdamped system does not have any overshoot. It just comes right back to equilibrium. Overdamped, it comes back very slowly. As I move towards the critically damped value, the critically damped is the fastest return to equilibrium without overshoot. Now here's an example for you, a worksheet for you to find the value for C in terms of the coefficients or the parameters that I show to give you critical damping. And I've included the solution in the module handouts. And so with that, a summary: we solve for the roots of the characteristic equation for a simple single degree of freedom system undergoing free damp vibration. We've defined the critical damping constant, and we've classified the different cases of damping and given you some examples. And with that, I'll see you next time.